Welcome to the second part. Now we are discussing an important concept, that is the combination of the resistors. Whenever the resistance of the circuit has to be increased, then we can combine different resistors in the series. But when we have to decrease the resistance of the circuit, then different resistances can be combined in the parallel. So we are to find a mathematical expression with the help of which, if we are combining few resistance in either series or in parallel, then how the net resistance or the total resistance can be obtained from the given combination that we want to determine. So here in the circuit you can see three resistors R1, R2 and R3, which are connected with a battery having potential difference V. You can see that the battery is going to supply a current I, and this current I, when leaves the positive terminal of the battery, the same current flows through the resistance R3, through resistance R2 as well as through resistance R1, and then it enters back into the negative terminal of the battery. So resistances all have the same current, so this is a series circuit. Now we want to find the equivalent resistance of R1, R2 and R3. If we use Ohm's law says that V is equal to IR, I is equal to V over R. So whatever current is flowing through the circuit in this case, it is the ratio of total voltage divided by the total resistance of the circuit. That means R1, R2, R3, they combine together to form a net resistance. If instead of using three different resistances R1, R2 and R3, we use a single resistance RS and we combine it with the same battery of potential difference V. In this case, after completing the circuit, if the current flowing in the circuit is also the same as that of the current flowing here when R1, R2, R3 are connected in series with the battery, in that case the function of the resistance in the circuit, both the figures is the same. That means same current is flowing. So if this condition is satisfied, then RS is playing the same rule as it is played by R1, R2 and R3 when they are combined individually in the circuit. So instead of using R1, R2, R3 separately but together in the circuit connected with the battery V, we can use a single resistance RS connected with the same battery in order to obtain the same current. So in this case, net RS will be equivalent or the net resistance of R1, R2, R3. We want to find equation for RS connecting with R1, R2 and R3. If we use Ohm's law from the circuit, because all the resistances are same, having the same current but different value, this means that voltage produced across each resistance, it will be different. Across resistance R1 voltage, it will be V1, which will be equal to IR1. For resistance R2 voltage will be V2, which will be equal to IR2. For third resistance voltage will be V3, it will be equal to IR3. So here V1 is equal to IR1, V2 is equal to IR2 and V3 is equal to IR3. From the second figure, we can write down V is equal to I into RS. Now, this circuit is working according to law of conservation of energy, which says that total potential supplied by the battery, it must be equal to the sum total of the potential difference across each of the resistance R1, R2 and R3. That is, V must be equal to V1 plus V2 plus V3. So if this is the case, if we substitute the values of all the V's, we will have I into RS equal to IR1 plus IR2 plus IR3. I into RS, I can be taken common, R1 plus R2 plus R3. I get cancelled, RS comes out to be equal to R1 plus R2 plus R3. This is the mathematical expression we were searching for, which says that in series combination, the net resistance is simply obtained by having the algebraic sum of the individual resistors. For example, if the resistance is connected in the series, they are having the value 2 ohm, 3 ohm and the 4 ohm, then their net resistance Rs will be equal to 2 plus 3 plus 4, that will be equal to 9 ohm. So important features of this series circuit is that current in all the resistance, all the elements will be same, but the potential difference of the battery, it will be divided among the different resistances, with the condition that if we add up the potential difference of all the resistances, it must be equal to the applied potential. Net resistance is simply the algebraic sum of all the individual resistances, so net resistance increases. This is the resistance in the series. This figure next is showing the parallel combination of the resistances, in which R1, R2 and R3, they are connected in parallel with each other with a battery with the help of a key. Now, if resistances are placed parallel to each other, if this is the first resistance, second resistance and third resistance, if the resistances are placed parallel to each other, you connect their same side terminals with each other. In that case, we call this as the parallel combination. Such combination is right in front of us. The battery positive terminal is connected to the point A, negative terminal is connected to the point B. Now these point A and B, they are known as the junctions. What is a junction? Junction is a point in a circuit where either the current is going to divide or either the current is going to be added together. So you can see that when battery supplies a total current I, when it reaches at the point A, the current has to always come out from positive terminal and enter back into the negative terminal. Now you can see that when current reaches at the junction A, now it has to go into the negative terminal, for which it has to first reach at the junction B. But in order to reach at the junction B, it has three conductive paths available to it. One by passing through R1, then R2 and then R3. So what is happening over here, that when current has more than one path available for the flow from one point to the another point, then that circuit is known as the parallel circuit. So parallel circuit is starting from point A and is extended up to the point B. So when current is reaching at the junction A, it divides itself into three parts. I1 flows through R1, I2 flows through R2, I3 flows through R3. Because I1, I2 and I3, they are actually the parts of I. So when all of them they reach at the point B, because B point is receiving the current I1, I2 as well as I3, so all the currents, they will all add up together and they will again produce net current I equal to I1 plus I2 plus I3, and this net current I, it will again enter back into the negative terminal of the battery. So this parallel circuit is behaving, having its property opposite to that of the series circuit. So whereas in series circuit current was remaining same, here the current is dividing. In the series circuit, potential difference was divided among different resistances, but here you can see that potential difference across each resistance will be same as that of the applied voltage. Reason, you can clearly see that every resistance is directly connected with the positive and the negative terminal of the battery. So you can see that if this is the positive terminal of the battery, it is connected at the point A with the resistance R1. So first resistance is connected with the directly with the battery, so its voltage is same as that of the battery. You can also see that second resistance is, two terminals are also directly connected with the battery, so its voltage is also same as that of the battery voltage. Third resistance, two terminals are also directly connected with the positive and negative terminal of the battery. So here again voltage is same. So in case of parallel circuit, voltage same but current divides. So if we use Ohm's law, V equal to IR, then for different resistances we can write down V is equal to I1 R1, V2 equal to I2 R2, V3 equal to I3 R3, where V1, V2, V3 are the potential differences for R1, R2, R3, and all are equal to each other. We are trying to find a net resistance, equivalent resistance. Suppose Rp is the equivalent resistance, P for parallel. That means here when Rp resistance, single resistance Rp is connected with the same battery V, then current flowing in the circuit I is same as it is supplied over here in the first circuit. So then Rp will be the equivalent of R1, R2, R3. So if this is the case, then V is equal to I into Rp. Now here the basic property of the circuit is division of the current. Its circuit is working on the basic principle of law of conservation of charge. The total charge supplied is always remains constant. So if battery supplies a total current I, it is getting divided into I1, I2 and I3 such that sum total of 3 must be equal to I. If we substitute the values of different i's from the equation we have just written, from this equation V equal to IRP, we will have V over Rp equal to I1. I1 value will be V over R1. Now I am writing V over R1. Reason, because V1, V2 and V3 all are equal to each other, which will be equal to V over R2 plus V over R3. V is same, so V get cancelled. So we have 1 over Rp equal to 1 over R1 plus 1 over R2 plus 1 over R3. This is the net equation we were trying to search, which says that reciprocal of the equivalent resistance is equal to the sum of the reciprocal of the individual resistances. So in this case, the net resistance of the circuit is decreasing. So whenever resistance are connected in series, we tend to increase the resistance, but in case of parallel, they tend to decrease the resistance. So in this case, if the three resistance connected with each other, they are 2 ohm, 3 ohm and suppose 4 ohm, then their net resistance will be 1 by Rp equal to 1 by 2 plus 1 by 3 plus 1 by 4, which will be equal to, first we take these two, 5 by 6 plus 1 by 4, it will be equal to 13 by 12, or Rp will be equal to 12 by 13 ohm. So net resistance is 12 by 13 ohm. You can see that here net resistance is getting decreased. Now an important feature of the both the circuits, you see that when we added 2, 3 and 4 ohm in the series circuit, net resistance we obtained 9 ohm. The greatest resistance present in the combination was 4 ohm. So you can see that in series the total resistance comes out to be even greater than the greatest, that is 9 ohm is greater than the 4 ohm value. Opposite thing happens in case of parallel circuit. In case of parallel circuit, you can see that out of 2, 3 and 4 ohm present in the combination, 2 ohm is the least resistance, minimum resistance present in the combination. So whenever you find the net resistance of the parallel combination, the net resistance becomes even smaller than the smallest. So you can see that 12 by 13 ohm, which is the equivalent resistance, is even smaller than the smallest value, that is 2 ohm. So the series and the parallel circuit, they behave exactly opposite to each other. Thank you.